All right, let's talk about indicator variables. So far the models that we've included have only had numeric or quantitative variables, by which I mean we were able to construct these design matrices out of the numbers for these different variables. So what would be an equation for predicting y from x when x is numeric? Well, that would just be y equals x beta plus epsilon. But what happens now if x is categorical? And so what would the equation be, for example, to predict y from x if x is a category with 2 levels? So if it's something like a binary variable. Or what would it be if you had x was categorical with 3 different levels? And so this is where indicator variables come into play. So an indicator variable uses 2 values, usually 0 and 1, to indicate whether a data case either does or does not belong to a specific category. There's different terms for this. So indicator variables, I think, is a common way to describe this. But dummy variables is another one that sometimes people use. Or for some reason in data science, they call this one-hot encoding, I think. And so these are all describing the same process. So here's an example. This comes from the Stat2 data package, and this is the diamonds data set. And so we've got this data set that looks at different prices for diamonds based on their color, their cut, their carat, etc. And so the column we're going to be focusing on for this lecture is the color column. And so you'll notice it has different categories, E, F, H, F, D, G, etc. And so the color category has different. The color variable has different categories, multiple different categories. And so if you were trying to create a design matrix, you obviously couldn't just input these individual values. You could not input these like letters into a design matrix, because how do you multiply letters? That's not possible. So we're going to have to do something else, which is where indicator variables come in. Okay, so what would this line of code do if you're just sort of trying to guess what this does? So I'm taking the diamonds data and I'm creating a variable called color D. And if the diamond color variable is equal to D, then this is going to have a value of 1 and it's going to be 0 otherwise. And so what I've done here is I've created an indicator variable indicating whether the color of the diamond is D. And similarly here, I've got a second indicator variable indicating whether the color of the diamond is E. And so this does the exact same thing, except instead of checking for whether the color is D, it checks for if it's E. And so we would do this for every single potential color or every single category. For that variable, we create an indicator variable for each of these categories. So in this case, from D through J. And it looks like this in our data set. So now I've got my color column still, but now if I look across all of these newly created variables, these indicator variables, they're either going to be 0 or 1 depending on the value. So in this case, in the first observation, the color is E. And so all of these indicator variables are going to be 0 with the exception of color E, which will be 1 to indicate that the color is E. And so this is how you convert a categorical variable into a numeric variable. Similarly, for the second one, the color is F, and so everything is 0 except for the color F column. That's going to be 1. For the color H, everything will be 0 except for the color H column, and so on and so forth. And so that's what an indicator variable is. It's just a variable that indicates whether or not the value is in that category. So if I wanted to model the relationship between total price and color, what would I do? So here, when I fit this model, I'm including all of these indicator variables, color D all the way through color J. And I end up with these different estimates, beta coefficients for each of these indicator variables. But one of them is missing. Why is this color J missing? So when you're including an indicator variable in a model for K categories, you always want to include K minus 1 indicator variables. Because if you recall from our what we've learned so far about models, is we want X transpose X needs to be invertible, which means that the columns cannot be completely dependent on each other or full linear combinations of each other. And if you include all of these, if you imagine that design matrix, you can perfectly predict that final column, color J, from all of the others, because if every other value is 0, then you know that color J must be 1. And if one of these other values is 1, you know color J must be 0. And so because this final predictor is perfectly predictable from the previous ones, you need to leave it out. And what that does is it makes that category the reference category. So here I've refit my model and I've appropriately left out one column or one indicator variable, in this case color J. And so the interpretation here is going to be a diamond with color D compared to color J increases the expected total price by $3,632. Or, for example, I could interpret this beta coefficient: a diamond with color E compared to color J increases the expected total price by $2,423, and so forth. What would be the interpretation for column F? A diamond with color F compared to color J increases the expected total price by $7,224. Okay, so what would the design matrix for this look like? It's going to look like this, where the first column still contains ones, like we always do. So the first column is going to be for that intercept. And then the subsequent columns are going to contain either zeros or ones, depending on if the value for that variable is indicated or not. So for example, this column could be associated with color D, this one with color E, this with F, and so on. So how many columns is this design matrix going to have? It's going to have the number of indicator variables minus 1 for the referent. So you're going to use the number of indicator variables minus 1. So you're going to drop the referent category. And then plus 1 for the intercept. So essentially it ends up having the same number of columns as there are indicator variables if you just have one categorical variable in your model. Now, if you have more categoricals in your model, variables in your model, or more variables in general, of course, then it's going to be bigger to account for those additional variables. So it turns out R is smart, and if you just do this, where you fit a linear model of total price on color, and color is a factor variable or a character variable, by default, R will drop one of the categories and make that the referent category. And by default, it's going to drop the first level. You may have noticed this when doing some of your modeling that had just two categories. This may have come up. So here, what is the reference category? It's going to be category D. And so now we would interpret this value as having color E compared to color D yields an expected total price of negative 1,209. And what if we wanted a different referent category? Well, we could code the indicators ourselves. That's one way to do it. So we could code up these indicators and then just leave the run that we want to be the referent out of the model. Or we could change the levels with the levels function in R. Okay, so I want you to do an application exercise. What I want you to do is I want you to create a design matrix X from this data here. So this data has a Y variable in the first column, so an outcome, and then it has a categorical variable age. And so what I want you to do is I want you to transform this categorical variable age into an indicator, into a number of indicator variables. And then I want you to use those indicator variables in a design matrix X. And then I want you to use that design matrix X along with a vector Y to estimate beta coefficients for predicting Y from age.